Hello, everyone. We are here in another weekly live that happens every Tuesday at 10 p.m. London time. And today we're going to be talking about the key value data structure. And in Java, it's more well known as HashMap, right? So we're going to be discussing here some of the core concepts of what is a key value data structure. And obviously, we're going to see this same data structure in basically all programming languages because it's a fundamental concept. And we're going to be exploring here some of those core concepts first in the mind map. And then we're going to see some concepts in practice with some popular algorithms that we have in code interviews. We will also explore how the hash collision happens in Java. And we're going to explore also how the HashMap class works behind the scenes. Obviously, we won't be doing a deep dive into the HashMap class because it's too many things, but we're going to be analyzing the main topics of the HashMap class. We're going to be exploring here as well the big O notation from the key value data structure in Java. So let's start then from the mind map. So what are the core concepts of a key value data structure? So the first thing to keep in mind is that the keys are unique identifiers. So you can't have two keys with the same value. And the values, they are associated to the key, right? And the key value data structure is also an abstract data type. So it's just a concept, right? So basically there are a couple of conditions here. If data structure is this abstract data type, and the key value data structure is also called as associative arrays, dictionaries, or maps. And it makes a whole sense, right? Because every element from this array, they are basically a key and a value, right? So I'm going to show you behind the scenes that actually a hash map is an array behind the scenes, right? So, and what are the operations in time complexity from a hash map? So the insertion in the average case is O1. But then when collision happens, we have O log n for tree-based data structure. So why is that? So if there are too many elements in the same bucket, what happens is that the data will be handled with red-black tree, with a balanced tree. So this is very interesting because it will make the code more performant, and also depends, right? Because if we don't have many elements in the bucket, a linked list will be used. But with a balanced tree, it's a lot faster to search for elements. And the lookup of elements for hash tables is O log n for tree-based hash map, right? And to delete, it's O1 as well. And if the element is in the bucket, so I'll show you in this how it works, how this collision happens. But basically, in a hash map, there'll be several buckets. And if this hash map collision happens, we're going to have several elements in the same bucket, So, which makes the deletion or any other operation slower. And to iterate on the elements, it's ON. Because we're going to have to iterate, it's a linear search. There's nothing we can do on that. Or to say it more specifically, it's a linear iteration, right? Not a linear search. Okay, and what are the implementation types? There are a couple of types here. So there's first the hash tables, and the hash table use the hash function to compute index, which means that the array index will be computed with a function behind the scenes using the hash code. And with hash tables, we can access elements with O1 if there's no hash collision. We have also collision resolution strategies. So for example, in Java, we use either a linked list or a balanced tree, which is the red-black tree. And with the balanced tree, we have the time complexity of O log n. So it's more efficient, right? And there is also load factor that affects performance. And we also have tree-based maps. So it's what I said here, right? So the red-black tree, it's used in Java's HashMap for handling collisions in buckets. So for example, if we use a red-black tree, we can make the algorithm more performant. And so instead of having OM, we're going to have O log n time complexity for worst case scenarios. And again, we won't go deep into red-black tree because this would be another whole class. So like we have also AVL tree, which also increases performance from ON to O log n. We have B-tree, which is a self-balancing search tree. And with those trees, we have guaranteed O log n operations. We also have skip lists. So we also have these skip lists, and it's usually used for probabilistic data structure. And what are the hash table components? So for collision handling, we have chaining, right? So basically, what is chaining? I'm almost sure that most of you here saw the chain of responsibility design pattern, right? So there is one reference inside the other. So it's similar to that. Like if you've never seen how a linked list works behind the scenes, so it's basically one object chained in the other, right? So that's how a linked list works. So it's a node inside another node. And then the other node has a reference to the next node and so on. So it's basically a chaining of objects. And there is linear probing. So there are plenty of concepts here that we don't really need for coding interviews. Like only if you really need to write a whole HashMap class, you would need to know all of those concepts. But like we don't need to go very deep into it, just the necessary for the interviews. So, and what are the common applications for HashMap? We can use a HashMap for caching, LRU cache, memory cache, database indexing, symbol table in compilers, implementing sets, counting frequencies, deduplication. So there are many uses for HashMap. And what are the language implementations? So in Java, we have HashMap, TreeMap, LinkedHashMap. In Python, we call all the maps as dict, dictionary, ordered dictionary. In JavaScript, object, variable name. We also have map. And C++, we have the name here, unordered map or map. Go is just maps, very simple. So, and what are the special variants? So we have ordered maps, right? So in Java, we have implementation for that, which is the LinkedHashMap. So it maintains the order. And for bidirectional maps, so we also have that, bidirectional maps, multi-maps, which is the case where we have many values for one key, right? So concurrent maps. So we have this concurrent hash map in Java to work on a thread-safe environment. Immutable maps, it's basically a map that can't be modified, can be modified after creation. And what are the performance considerations? So one of the most important concepts of a hash map is the hash function quality. Why? Because if we have a hash function that is different, for example, we create 1,000 objects and we have 1,000 different hashCode functions. This means that we won't have any collision in our hash map. And when we don't have any collision, we have an enhancement in performance, right? So that's the first thing. We need good quality hash functions. And what is the initial capacity? So in Java, for example, the bucket starts with 16, right? And there's also the load factor. So basically, when the hash map exceeds 75% of the current capacity, then the map will resize, right? And so for example, here we see here that like from Java 8 onwards, buckets convert from linked list to red-black trees. So basically, this improves the worst case lookup time from ON to O log N. And the memory usage, so there is some concepts here. So for the internal array, we have here the capacity versus the reference size, and the entry object is basically a key value. And on each entry, we have a pointer to the next object, right? And the memory increases when the load factor decreases. So this means that we're going to have more empty buckets. And again, like those specific concepts from HashMap, like those details, they are not really necessary to know for a coding interview. Like if you want, because you're curious, that's nice, but it won't even help you too much on your day-to-day job, unless you're working on developing a programming language, then it would be useful. But otherwise, it's not very useful. So HashMap, so okay, probably you know that, but in a HashMap, we don't keep the order. So that's the thing. So when you put elements in a HashMap, you don't keep the order of the elements. But a linked HashMap, it will keep the insertion order, right? So sometimes we need to choose, right, between a HashMap or a class. So in this case, the concurrent HashMap is thread safe, but obviously it's gonna drain performance a little bit more. And if you don't need order, if you don't need anything else, just use HashMap. If you're working in a multi-thread environment and you know that there could be a data collision, just use the concurrent HashMap, right? And okay, so basically those are the main concepts of the HashMap. Like I said, it's impossible to go very deep here because we don't have much time. And like this is not even the goal, because going very deep into HashMap won't really help you for interviews or even for your day-to-day job. So without further ado, let's explore the code. Firstly, the big O notation of HashMap, and then we're gonna see more code. Okay, so let's see the code then. This is the HashMap complexity. So this is really important for interviews. You need to know the big O notation. You need to know how performant is a HashMap, right? So this is a very simple example. And here, when we put key 1 and key 2, we're gonna have O1 of time complexity, right? Because there's no collision here, right? There's no hash collision. So in this case, we're gonna have O1. And here's the same, like since there's no hash collision, we're gonna have O1 as well. And for method, it's also O1, right? So, and if there is a hash collision, you see that it would be ON, because it would have to do a linear search in the buckets elements until we find the right object using the equals method. So it would have to do basically an iteration over each object and make this check with each element. And here in this map, so the contains method is actually ON because we are comparing the value, right? It's not the key. So the value so a looping has to be done, right? So yeah, if you can see here, notice that we are doing 2 loopings here. So, and as you can see, this is how basically a HashMap works behind the scenes. It's an array. It's an array of node. And in this node, we have the key and the value, right? So the key is a generic type, and we have the V for value. So, and here we remove, and since there's no hash collision, it's O1 as well. And to iterate over all the elements, it's ON. ON here as well. So basically, we're just iterating over each entry set, right? So, and here in this put all method, it's OM because we are inserting many elements. And to clear the whole HashMap, it's ON as well because we would have to remove all the object references. To get the size, it's O1 because it's basically just a property in the hash map or whatever is implementation of the map. It's just a property that we are reading, and this is the same. Is empty is also just, if you see this method, so it's just size equals 0. So and this is what I like for encapsulation, by the way, because like imagine if you had to implement this whole hash map in every application you are implementing. Imagine if you have to check if your hash map is empty and you would put this code all over your application. Like it would be horrible to maintain, right? And that's what I like of encapsulation, because you don't really need to know, like it could have like a horrible code here that, like if you basically read the interface and you know that this method is really doing what we expect it to do, that's all we need, right? But we are just checking here the code just, for didactic principles, right? So that you understand better what is a hash map behind the scenes, right? So if we see here, if you go to the top, you can see here that there is a node, element. This is the capacity of the bucket, 16, right? The key, the value, the pointer to the next element. So it's very interesting to read the Java classes because you learn a lot, right? Okay, so obviously, the purpose is not to teach you the whole class, because like to teach the whole HashMap class, it would take like one whole class itself. So not worth it. But, let's see how the hash collision happens, right? Because I don't know if you are familiar with this concept, but this is important to know how it happens, right? So firstly, let's see a good HashMap object. So we have one value here, and like in this hashCode, we will have a different value, which means that this is a good hashCode implementation. If the hashCode values are different, when the values are different, it's a good hashCode implementation, right? Because then we won't have hash collision, right? So let's start with the good hash object. So first, let's just run the code and then I can show you. So check this out. So the insertion time for 10K elements, it's 1.34 milliseconds. And the lookup for 1000 elements, it's 0.23 milliseconds. But now with hash collisions, look how horrible the performance is. So the insertion time for 10K elements is 187.14 milliseconds. So the same operation is 187 times slower than if we don't have hash collisions. And the lookup time for 1000 elements is 20.78 milliseconds. So it's more than 20 times slower. It's horrible, right? So that's the impact of having a bad hashCode method. And now you might be wondering, okay, Rafael, what is a bad hashCode method? So a bad hashCode method is basically a hashCode that returns the same value. So if we return 1 here, for example, like whenever we add this object, this bad hash object in our map, there will be the hash collision, right? So, which means that if we want to insert another element, we would have to iterate all the elements from the linked list, and we would have to put manually this object in this list, and the time complexity would be O(n). So it's really bad at performance. So I hope you understand the concept, and I will also share the code with you later, and also the mind map. So stay tuned. And now let's see some algorithms that we see in interviews very often. So let's debug it so that it's easier to understand. So basically, this algorithm, we want to check if the arrays have the same element, right? So firstly, we do some checks here for edge case scenarios. And during the interview, it's important that you ask the interviewer about that. And first, we're going to count the elements in the first array, right? So we have number 2. And what we are doing here, So basically, we are counting how many elements we have here. So for example, for number 2, like we're going to use number 2 as the key, and number 2 will appear twice, right? So in this case, we are counting here. So basically, what we are doing here, so this get our default method will get the value. And if this value is null, we're going to get 0, right? Then we're going to sum it to 1. And then once it's 1, then we're going to keep adding up the elements, right? So basically, what we are doing here, we are just creating a map where we count each element, right? So as you can see here, so let's keep debugging. So in this map, we have 5 elements. So number 1, we have 1. Number 2, we have 2. Number 3, we have 1 element. Number 4, we have 1. And number 5, we have 1 element. And then we check if this map contains number 1, for example. And here we decrement the values here. If we found the value, we decrement 1 by 1. And all counts here should be 0, right? So yeah, and we have all zeros, which means that all the elements are the same. This is ON, by the way, because we are iterating in a looping. So this is true. It's very simple algorithm, but sometimes you might have this algorithm in a coding interview. And there is this count characters algorithm as well. So let's see it. So as always, you check the edge case scenario. And here we're going to do basically the same thing we did before. So we're going to count each character. So this is even easier than the other one. So, and this function here is very important to remember, to-char array, right? Because you're going to have to deal with that in many string algorithms. So basically here we are counting the elements we find. So A, we're going to find it twice. So I'm going to show you the map, how it's going to be in the end. So yeah, basically A you find twice, letter C you find twice, letter F you find twice. So very easy, and that's it. That's pretty much it, this algorithm, right? So let's see this other one. This is a bit more complicated, but still it's fine to solve it. So basically, in this algorithm, we need to find the first non-repeating character in a string. So in this case, it's letter B, right? Because B is the first character that doesn't repeat here, right? So how can we solve this algorithm then? Let's see by debugging it. So we're going to iterate over the string array, and we're going to do the same, right? We're going to be inserting the key as the letter, as a character, right? And then we're going to be adding 1 for each character we find. So let's do that. Let's see what happens. So now we have this freak map, and letter A, we found it twice, and letter B, we find it once, C, once, F, we found it twice. So meaning that letter B is the right one. So in this case, so why it's important to know that the hash map is not ordered? Because, for example, if you're iterating the hash map relying on the order, there would be a bug on your algorithm because hash map is not ordered, which means that the elements are all, they're not ordered. Like sometimes they keep the same order, right? But it's not reliable, right? It's totally random. Okay, so in this case, we need to run through the array of strings because here we are sure that the order is correct, right? So, and then it's easy. Like once we iterate over the array, then we have the array ordered in an ordered way. And then we have all the information in the map, right? So like letter A, like is not equals to 1 because if you see here, letter A, we have 2A on this. And then, well, it's going to be letter B, right? So letter B is equals to 1, therefore it's letter B. So that's why it's so important to know the data structure because like doing this algorithm with another data structure other than a hash map would be more difficult, right? So, but if you know the right tool for the right problem, you're going to save a lot of code and it's just a lot easier, right? Like with the hash map here, you get all the characters, you know how many times the characters are in the string, and you just need to do a very simple logic here in the end, and that's it, it's done. And okay, so let's see the group anagrams algorithm. So what is an anagram? It's basically like words that have the same letters, the same characters, right? So for example, eat like has the same character. So if you read eat here and T, we have letter E, we have letter A, we have letter T, right? So it's the same with 8 because we have letter E, letter A, and T. So this is an anagram, right? So let's debug here the code and let's see how it works. So firstly, we instantiate a map and we have a string as key and a list as a value. And by the way, this is just the generic type, right? Because if you see here on the hash map, we receive two generic types here, right? So we receive the key and the value. And in our case, we passed a string and a list of string. Okay, so here we iterate on each string and we get the chars. And the thing is that we are sorting each array of chars. Then we have the sorted string. And basically we check here if this hash map doesn't have the sorted string, we're going to put the sorted string and we're going to instantiate a new array. And then here we get this sorted string and we add the string E. Here we're going to do the same thing. We're going to sort the string as well. And now we have it, right? So since we have this anagram contain this group, now we're going to add here, right? So this anagrams group, if we see what we have here. So we're going to add now. So let's see here. So in the array list, we have those two elements, eat and T. On this key AET, we have two anagrams already, right? And this won't be an anagram, right? But this is an anagram with that. So let's continue. So when we sort 10, we get ant. So since we don't have this ant as key yet, we're going to insert a new array list and we're going to insert 10, right? So an 8 is an anagram with those. So let's continue. So by sorting the string, we get AET. So we already have this key, right? So we'll just add the new string. So if we check our anagram groups now, so now we have 3 elements here, right? So let's continue here now. And bat is just bat, like it's not, won't have any element with that. Like we won't have any anagram here. So it's just a separate word. So which means that, look at the answer. So we have 3 anagrams for AET, and we have 2 anagrams for ant. And for bat, we don't have. We have just bat. And that's pretty much it. So as you can see here, we have eat, T, 8, 10, and nut, right? And as you could see here, the hash map is not ordered, right? It came in a random order here. So those are important details because this could be a reason for bugs, right? If you don't know that the hash map is not ordered, you might insert elements there and you might do a logic that you are relying on the order, and then it might work. Like sometimes it will work and other times it won't work because it's not ordered, right? So if you want to work with a map that is ordered, you can use the linked hash map. So, and let's also have a quick look in one of the cases that we would use a hash map. So one of the use cases would be to use it for cache, right? But basically those are the main concepts of the hash map class. And let me go back sharing another screen. So do you guys have any questions or it's all clear? So it's not that complicated, like to learn the hash map for the interview case scenario, because basically you just need to know the main data structures that will enable you to solve most of the problems for coding interviews. For example, all those algorithms I showed you, they are perfect to be used with key value data structure or HashMap or hash table. When I talk about key value data structure, is the same as those classes, because basically if you see the HashMap, the hash table, or all of those classes, they basically implement the fundamentals. And you're going to see the same in Python, in Golang, JavaScript, because it's all fundamentals, right? So that's pretty much it, guys. So thank you so much. I will share. Do you have the mind map? Who wants the mind map? I can share the mind map with you. So that's it, guys. Thank you so much for showing up today. And in the next Tuesday at 10 p.m. London time, we're going to have another weekly live. And it's going to be either about queues or stacks, maybe both. So I will let you know by email what data structure we're going to explore. And I'm going to also show you a couple of algorithms that we see in coding interviews. Okay? So thank you so much for showing up. And I'll be publishing the video very soon. And yeah, have a good night, everyone. And I'll talk to you soon. Cheers. Bye-bye. Thank you.